Diana has 800 yards of fencing and wishes to enclose a rectangular area. Express the area of the rectangle as a function of the width of the rectangle. For what value of W is the area the largest, and what is the maximum area? So we want to express the area of the rectangle as a function of width. So if we draw a rectangle to try to model this situation, a rectangle has a length and a width, and we can express the area as length times width. However, we want to express the area with only the variable W. So we're going to use this information about 800 yards of fencing. The fencing is going to refer to the perimeter of this rectangular area, and the perimeter will be 2 times the width plus 2 times the length. We know we're going to have 800 yards of fencing, so that perimeter will equal 800. 800 equals 2W plus 2L. So I'm going to solve for the length and then substitute into the length in my area function, so I can reduce the number of variables down to just having the variable of width. So I'll subtract 2W on both sides. That gives 800 minus 2W equals 2L. Divide by 2, which gives L equals 400 minus W. And then I'll substitute into the area function. This gives 400 minus W times W, which is 400 W minus W squared. I'm going to write this in descending order so that it's negative W squared plus 400 W. So we've completed part A, in which we find the area of the rectangle as a function of the width. Then we want to know for what value of W is the area the largest. Now there are many strategies that we can use to determine this value, some using algebraic techniques, using a calculator, and also using calculator techniques. Calculus techniques. We're going to use an algebraic technique, and in this example I can recognize that my area function is a quadratic, and the graph of a quadratic function is a parabola, and this particular parabola has a leading coefficient of a negative, which means that it's a down-facing parabola. So that lets me know that the maximum value, the maximum area, is going to occur at the vertex. So I can find the vertex, and when I find the vertex, I'll be finding the value of W that gives the largest area. We have a formula to find the vertex. The vertex is an ordered pair, HK, and I can find the value of H using negative B over 2A. In this example, A is negative 1 and B is 400. So H is negative 400 over 2 times negative 1. That's negative 400 over negative 2, which is 200. So this is the value of the width. This is the width that produces the largest area. And then I can find the value of K. So I'll substitute 200 into the area function. This gives negative 200 squared plus 400 times 200. So this will be a negative 40,000 plus 80,000, which is 40,000. And this will be square yards. So the maximum area is 40,000 square yards. Determine whether the following function is a polynomial function. If the function is a polynomial function, state its degree. If it's not, tell why not. Write the polynomial in standard form, then identify the leading term and the constant term. We have g of x equals x to the 7/2 minus x to the 4th plus 5. I've written down here the definition of a polynomial function, and a polynomial function is of the form f of x equals a sub n x to the n plus a sub n minus 1 x to the n minus 1 plus ... that means and so on, meaning that the pattern continues. And the pattern that we're supposed to be looking at is that we had a power of n on the first term, and the next term has a power of n minus 1, so one less than the one before. And we continue that pattern until we get down to a power of 2, then a power of 1, and then no variable, which is a power of 0. So the key thing that we want to pay attention to is that n, that power on our x, needs to be a non-negative integer, which is 0, 1, 2, 3. So the powers are restricted to being these values right here. The powers on our variable x is restricted to these numbers. And looking back at our function that was given to us, remember we want to determine if this is a polynomial function. You can see that the power on x is 7/2, which is not on our list of values. So we can say that this is not a polynomial function. And because it's not a polynomial, we are not able to identify the degree and the leading coefficients and these other requests. Form a polynomial whose real zeros and degree are given. We're given zeros of -3, 0, 6, and we have a polynomial of degree 3. We have a theorem related to zeros and factors of a polynomial that says that when you have a 0 of c, then your polynomial will have a factor of x minus c. So we're given a 0 of -3. So that means that we have a factor of x minus -3, which is x plus 3. We have a 0 of 0, which means that we have a factor of x minus 0, or just x. And we have a 0 of 6, which means we have a factor of x minus 6. So we can form the polynomial by multiplying these factors together. So our polynomial is going to be f of x equals a. Now I'm choosing a because there's not just one polynomial with these zeros and factors. There are infinite polynomials, and we can find this family of polynomials with these zeros by multiplying by this leading coefficient. So we'll multiply the factors together, x plus 3 times x minus 6, and I'll rewrite this as a times x plus 3 times x minus 6 We can simplify this a little bit. I'll multiply x plus 3 times x minus 6, and that gives x squared minus 6x plus 3x minus 18. I'll combine like terms to give x squared minus 3x minus 18, and I'll also distribute the x. So that would give x cubed minus 3x squared minus 18x. You can notice that this is a polynomial of degree 3, and a polynomial of degree 3 has 3 zeros. If you consider multiplicity. Determine whether the graph could be the graph of a polynomial function. If it could be, list the real zeros and state the least degree the polynomial can have. So first we want to determine if this graph could be the graph of a polynomial function. The graph of a polynomial function will be smooth and continuous. So when we're looking at the graph, if we want to say that it is smooth, we should see no sharp turns, no corners, no cusps. No sharp turns, no corners, and no cusps. So no sharp turns, no corners. I think that's probably sharp turn, same as sharp turn. A cusp would be more like this. And looking at this graph, we see none of those things. So this graph is a smooth graph. It's also continuous. So with continuity, we're looking for no gaps, no asymptotes, and you can see that we have a curve that is continuous. We can draw the curve without picking up our pencil, and so this could be the graph of a polynomial function. So since it could be the graph of a polynomial function, we want to list the real zeros. So the zeros are the locations of the x-intercepts. So real zeros are going to be the same thing as the x-intercepts. We have a few points here where we have x-intercepts. It looks like to me -3, 0, and 5. So our real zeros are -3, 0, and 5. And we want to state the least degree. For the least degree, we're going to pay attention to how many turning points we have. We have a turning point here and here. And the least degree will be one more than the turning points. So since we have 2 turning points, the least degree is 3, one more than the number of turning points. Use the remainder theorem to find the remainder when f of x is divided by x minus 2. Then use the factor theorem to determine whether x minus 2 is a factor of f of x. We're working with the polynomial function f of x equals 4x cubed minus 13x squared plus 7x plus 10. So first we want to use the remainder theorem. The remainder theorem says that f needs to be a polynomial function. If f of x is divided by x minus c, then the remainder is f of c. So we have this polynomial function, and we want to divide by x minus c, which is x minus 2. That means we can calculate the remainder by calculating f of c, which in our example is f of 2. So let's calculate the remainder. f of 2 is 4 times 2 cubed minus 13 times 2 squared plus 7 times 2 plus 10. That gives 4 times 2 cubed, which is 8, minus 13 times 2 squared, which is 4, plus 7 times 2, that's 14, plus 10. 4 times 8 is 32. 13 times 4 is 52. And 14 plus 10 is 24. 32 plus 24 would be 56 minus 52 gives us a remainder of 4. So the remainder of f of x when it's divided by x minus 2 is 4. So in the second part it says use the factor theorem to determine whether x minus 2 is a factor of f of x. So I have the factor theorem here. Let f be a polynomial function, then x minus c is a factor of f of x if and only if f of c equals 0. So remember, we just divided by x minus c, and we calculated f of c to be the remainder, and if that remainder is equal to 0, then we know that x minus c is a factor. So we got f of 2 to be 4, so the remainder is equal to 4, and since that remainder is not equal to 0, that means that x minus 2 is not a factor of our polynomial 4x cubed minus 13x squared plus 7x plus 10.